To describe how objects move between two events, we use the ideas of average velocity between two events and average speed between two events. Here we're working exclusively in 1D. The SI unit for velocity and speed comes from the SI unit for distance, meters, and the SI unit for time, seconds. So all our velocities and speeds will be measured in meters per second. You must convert all velocities and speeds to meters per second when doing your calculations. Let's return to Chewy's adventure. Here again is the map of the one-dimensional world Chewy is moving around in. We're familiar with these 6 different events in the course of his day, moving from one place to another. Let's add to this map a timeline showing that at event 1, when he left his treehouse, he started his clock, and let that be his reference point of 0. So time is 0 at event 1. We're going to pretend, to make this easy, that Chewy didn't spend any time hanging around at the gas station or at the petting zoo, that instead he left the moment he arrived. So on our timeline, we have 6 times marking the times of each of these events. So when Chewy arrives at the gas station, that's event 2, he arrives there 126 seconds after he left the tree, and we'll assume that he immediately departed to go from event 2 to event 3. Okay, so once we combine a map with a timeline, we can have information about the motion of the object during that time. And we want to define this idea, average velocity, between any 2 events. Any average that you ever take has to be between 2 different events. We define the average velocity to be the displacement per unit time. We use lowercase v to represent velocity, little av to indicate average velocity. We'll have a different concept, instantaneous velocity, later, so av to indicate the average. And displacement is delta x, the change in position, divided by the change in clock time, our time interval, delta t. Let's calculate a few examples. His average velocity between events 2 and 3, arriving at the gas station and then immediately departing, arriving at the petting zoo. Average velocity definition is delta x over delta t, displacement over time. His change in position, well, he ended up, his final position was at 1534 meters, minus initial position, 835 meters. And his final time, T3, was 200 seconds, and initial time, T2, 126 seconds. So the change in time on the clock and the change in his position from going from here to here. So final position minus initial position. That's 699 meters divided by 74 seconds. Put that into the calculator and you get approximately 9.4 meters per second. I use these 2 squiggles to indicate approximately, meaning we rounded this value. I rounded to 2 significant place digits because we have 2 sig figs in 74 right here. Okay, so his average velocity between those 2 events, 9.4 meters per second. It's positive value because he moved in the positive x direction over that time. Another example. His average velocity between events 3 and 5, going from the petting zoo to the barbershop. Average velocity is displacement over time interval, delta x over delta t. His final position was negative 992 meters. His initial position was 1534 meters, so final minus initial. And his ending time at event 5 was 368 seconds. His starting time was 200 seconds. So final minus initial, 368 minus 200 seconds. That's negative 2526 meters divided by 168 seconds, which is approximately, because we're going to round, negative 15.0 meters per second. I kept 3 sig figs here because there's 3 sig figs in the time down here. All right, notice this time the velocity is negative. His displacement was negative, thus his velocity is negative. Between those 2 events, Chewie moved in the negative x direction. So velocity tells us something about the direction of motion. A positive velocity means we moved in the positive direction. A negative velocity means we moved in the negative direction. One more example of average velocity between events 2 and 4. Okay, delta x over delta t, displacement over time interval. Final position was 835. Initial position was also 835. He ended up back where he started. Change in time, well, event 4 occurred at 261 seconds after 0. Event 2 occurred at 126 seconds after 0, so the change in the clock time, 0 meters over 135 seconds. His displacement was 0, therefore his velocity was 0. He was moving between those two events, but because he ended up where he started, his total change in position was 0, therefore his total velocity, the average velocity, is 0. So velocity can be a positive, negative, or 0 valued quantity. If you end up where you started, your velocity is 0. Okay, the next idea, average speed between two events. Slightly different, but this is related to the difference between displacement and distance. The average speed between two events, and we can represent it by a lowercase s with a little av for average, is your distance traveled per unit time. So distance traveled divided by time interval. Best way to think of average speed is as the average reading on your speedometer in your car as you're traveling. This is your average speedometer reading. That's what we mean by speed, to distinguish it from velocity. Okay, so let's figure out what your speedometer would say on average as you're traveling between events 2 and 3. To get our average speed, we need the total distance traveled divided by the total time it took. So between events 2 and 3, we moved 699 meters, and we already know that that took 74 seconds. 699 meters divided by 74 seconds, about 9.4 meters per second. Notice in this case, our average speed is the same as our average velocity. It's not always the case. Let's look at the next one. Let's check out our average speed between events 3 and 5. So we need our total distance traveled divided by the time it took. Now here, between events 3 and 5, the distance traveled was this 1534 meters from here to here, and another 992 meters from here to here. So we moved a total of 1534 plus 992 meters, and we know that from 3 to 5 took 168 seconds. .34 over 168 plus 992 over 168 comes out to about 15.0 meters per second when we round. Notice the difference between the average speed between events 3 and 5 and the average velocity between events 3 and 5. The average speed is positive, average velocity is negative. Speed is always a positive quantity, because your speedometer doesn't know whether you're moving forward or backward, whether you're moving east or west. All it's recording is the rate of travel. So speed is always positive. Your velocity has that directional information, a negative sign there to tell you you're moving in the negative direction. Or velocity can be 0 if you ended up where you started. Let's see, how about one more example for average speed over here between events 2 and 4. Distance traveled over the time that it took. So between events 2 and 4, we moved 699 meters this way and 699 meters back that way. So our total distance traveled was 699 plus 699 meters. The time it took we know is 135 seconds. So that comes out to be approximately 10.4 meters per second. Compare the average speed between events 2 and 4 to the average velocity between events 2 and 4. You ended up where you started, so your velocity is 0. But you were moving the whole time, and if you were watching your speedometer while you were moving, you would have noticed it didn't say 0 the whole time. It said some value, and on average, that value would have been about 10.4 meters per second. Okay, well, actually, your speedometer in your car doesn't say meters per second. It says miles per hour. And we want to have a sense of, well, how fast is 10.4 meters per second? How does meters per second compare to miles per hour? So you need to do a conversion. To convert from meters per second to miles per hour, or vice versa, let's consider this. If we start with 1 meter per second, and we could look up that there are 1609 meters in 1 mile, and we already know that there are 3,600 seconds per 1 hour. You have that memorized by now. So let's cancel off factors. Meters cancels meters, seconds cancels seconds, and we're left with miles per hour. So 1 times 1 times 3,600 divided by 1609 gives us 2.24 miles per hour. In other words, 1 meter per second is equivalent to about 2.24 miles per hour. But here's what I want you to memorize. Let's round this to about 2. So 1 meter per second is about 2 miles per hour. A good thing to have in mind just to make ballpark estimates. Okay, so let's make some ballpark estimates here. If our average velocity was 9.4 meters per second, we know every meter per second is about 2 miles per hour, so we can about double it to figure out what that speed would be in miles per hour. 9.4 meters per second, that's going to be about 19 miles per hour. I use the 1 squiggle to indicate we're making a very approximate ballpark estimation without even using a calculator, just in your head. 15 meters per second, we can about double that to figure it's about negative 30 miles per hour. And of course, 0 meters per second is 0 miles per hour. Down here on the speeds, 9.4 meters per second. Again, we can about double it, about 19 miles per hour. 15 meters per second, double it, it's about 30 miles per hour. And 10.4 meters per second, it's going to be about 21 miles per hour. Okay, I want you to practice some of these on your own. Pause the video for a moment and work out Chewy's average speed and his average velocity between each of these pairs of events. And then when you're done, then estimate each of those in miles per hour. So in your head, convert from meters per second to miles per hour using that approximate value of 1 meter per second is 2 miles per hour. Okay? Ready? Here are the answers.